our notes dealing with related rates. My plan for today is I was going to show you a second way we could have done that problem C from yesterday, just to give you options. And again, I don't really care how you do a problem as long as you do it correctly. And then I wanted to look at one more example, that last one, dealing with a cone that's going to require similar triangles. To kind of remind us where we're at with related rates, the main idea behind these related rates problem is that they do have pretty much like, I don't know, like a process you kind of go through, certain steps you want to look for. The first thing to look for is kind of look at your given information. They'll give you like a moment, they'll give you some rates, and so that's kind of the givens that you use to solve the problem. Then you'll need to find a relationship. That relationship could be a geometric formula, it could be an equation that's given to you directly, or it might be just something you have to figure out the relationship using like maybe a combination of your knowledge of geometry and things like that. And then you're going to take the derivative. For related rates problems, we always take the derivative with respect to time, with respect to the t variable, plug in your knowns, and then solve for the unknown. And most of the time in these problems, you're solving for an unknown rate. So we had ended the class period on C. And in C, we were talking about how we could find the rate of change of the angle for this triangle with like a ladder sliding down the wall. And I showed you the example where we wrote like a regular trig equation. And technically you could have written any trig equation, so like sine, cosine, tangent, or even cosecant, secant, or cotangent. We want to choose the easiest one, and to me, doing a sine of theta problem is the easiest. So the problem that we solved yesterday was sine of theta is equal to that b over the 13. A second version, or a second way that we could have also done that problem, just to give you options, is instead of doing like a trig problem, we could have done an inverse trig problem. So instead of saying like the sine of theta is equal to b over 13, you could have simply said that theta is equal to the arc sine, or inverse sine, of b over 13. That equation is identical to the one we did yesterday. We're just kind of flipping around using sine versus the inverse of sine. We can still take the derivative implicitly. So the derivative of theta will be 1 d theta dt. I think this version is nice because d theta dt is already isolated. And then we do know the derivative of arc sine. The derivative of arc sine is 1 over the square root of 1 minus the inside squared. Don't forget the chain rule, times the derivative of the inside. B over 13 is like 1/13 of b, so its derivative will be 1/13, and then we have db dt. So definitely a much more complicated derivative than what we did yesterday. This one, though, I think is easier in some ways. Like, you have everything to plug in, like we know what b is, we know what db dt is. Whereas in the other way, we had to go back to the triangle to figure out what the ratio of the cosine of theta was. But we would get the same answer. It's like plugging in my values. I have 1 over the square root of 1 minus. The b value, I already forgot what it was 12. And then we had 1/13, and then db dt was given, and that was 2, and that's from the original problem. I know this looks completely different from this answer, so definitely not simplified when you plug it in, but I promise you, like, you can check yourself, check me, they are the same answer. They look very different, but they do end up working out the same. Again, I don't care which way you would do an angle problem. I prefer this way just because your final answer always ends up being simpler. But if you don't remember how to find cosine of theta, this way you don't have to worry about going back to the triangle. You just take the derivative and plug in the parts that you have. Questions on that? All right, so the one that I really want to focus on today is this one. This was the last one you saw listed. So the AP exam loves a related rates problem dealing with a cone or dealing with like water draining out of a tank. Like whatever it is, the writer of the AP exam loves those types of problems. So this one combines both of them. We have a cone that is a tank that's draining of water. So remember when you approach these problems, I kind of like look at the givens and then kind of look at what I have. the relationship I have, and then make sure I have everything I need to find what it's asking me to find. So we have this tank that's a cone, and it has a diameter of 40, and then its height is also 40, so not quite drawn to scale, but the diameter and the height is 40 for this. It says water is leaking out of the tank at a rate of 80 cubic feet per a minute. So if water is leaking out, and that is cubic feet per minute, that is a value that represents the change in volume over the change in time. So we've been given basically dV/dt. Do you want to be careful, since the water is leaking out, the rate is actually going to be the 80 cubic feet per minute. And then we want to find the rate of change of the water's height. So we're looking for dH/dt at the moment when the water is 8 feet deep. So we're looking at it for when the height is 8 feet. Include units in your answer. And yeah, so that's what we have. So if I'm looking at this problem, like they give us the volume formula, you might have already known that, but they give it to you. And so I see that V is equal to 1/3 pi r squared h. Does anyone see, just kind of looking at this problem, some issues we might run into with what we were given in this problem and like the relationship that we have? We have nothing in there about r. Like, we don't know what r is. We don't know what dr/dt is. Like, we know absolutely nothing about r. Even if you didn't recognize that now, I'm going to go ahead and do the derivative. Like, will be the wrong way to do it. So write it down if you just want to. But if I was finding the derivative, I would have to use the product rule because I have two variables being multiplied. So in doing the derivative, that's going to become dV/dt is equal to 1/3 of pi is just a coefficient. So I have the derivative of the first times the second plus the first times the derivative of the second. So not the prettiest derivative, we would need to use the product rule. And then the issue that we kind of noticed, so like I have dV/dt, 2/3 pi is now a coefficient. I don't know anything about r. I don't know anything about dr/dt. I do at least know h here. Again, I don't know what r is. And then I'm trying to find dH/dt. So I basically have too many unknowns in my problem. Did I mess up somewhere?
No. Could you use the diameter to find radius?
Yeah, so we would eventually get there, yeah. I'm not there quite yet. And also you want to be careful. So this is that 40 is the diameter of the full tank. So like the radius of where we're actually talking about for that moment is not like the consistent.
Would it be proportional then?
Yes, that's exactly where we're kind of getting at. So what Matthew said for those at home, like, isn't this proportional? And the idea behind these problems is, yes, that's what we have to kind of recognize. So especially for geometric shapes, it happens in triangles, but like anytime you can find a proportion or like how they are directly related by a ratio, we can simplify the problem. And you actually wouldn't, so yes, we could see, you know, like looking at the full tank is pretty easy to see. So the full tank is like the radius of 20 and the height is 40. So you can kind of see like the height is always going to be double the radius. And you could use that to find the r value. The issue is we still don't know what dr/dt, because we can't really like, don't necessarily know how the rates are going to be related to each other. So the idea behind this problem is we want to go back to our relationship and see if we can rewrite it by eliminating variables. So the way that we are going to eliminate variables is we are going to use similar figures. And I kind of always look for triangles. So we have like the whole part, the whole to the part. Our part to the whole doesn't really matter how you set up your ratio. So if I'm looking up a similarity equation to have, so I know that for the full cone, it had a radius of 20, but r can be changing as that water drains out. Then for the full cone, it has a height of 40, but that height is going to change as the water drains out. This one's a little bit easier to see just because the numbers, but we can go ahead and cross multiply. 40r is equal to 20h. I don't know anything about r, so I want to get rid of my r's. So R is equal to 20H over 40. Our R is equal to 1/2 of H, which many of you can look at that diagram and see that relationship. But where that relationship comes from, instead of plugging that in after taking the derivative, we can plug that relationship into the original relationship and basically write a new formula for the volume that's just in terms of H and no longer in terms of R. And so what I mean by that, give me some more space. Here's the R, that's the R that we don't really know anything about. We don't know anything about its rate directly, but I can now rewrite this problem and now say that volume is equal to 1/3 of pi. What is R? R is always 1/2 of the H. And then obviously don't want to take the derivative with it written that way. We can simplify our relationship. It's going to have an easier derivative. 1/2 squared is 1/4. 1/3 times 1/4 is 1/12. I'm just going to put the pi up there so I can kind of see it clearly as a coefficient. H squared times H gives me H cubed. So I have now a much more friendlier equation to use for volume. Again, to be clear, that's not the equation for volume for every single cone. That's just the equation for this particular cone that has the given dimension. So this is the one where the height was always 1/2 of the radius. Or the radius always 1/2 the height, if I say that correctly. So now go ahead and finish out that problem for me. So we've eliminated the R. Now we can go ahead and take the derivative implicitly, plug in our given, solve for the unknown, and then make sure you include the correct units. And again, feel free to leave your answer as ugly as necessary. Go ahead.
Mr. Brown,
Yeah.
could you go over how you got that H over 2? Because
Like how I set up my proportion.
yeah, I was just confused how you did that.
I set it up by looking at part to whole is equal to part over whole, like similar shapes from geometry. And so when I'm looking at, there's like the R and the H. So I
Yeah,
had
I got you. I just don't remember geometry, so my bad.
See it. So finishing up this problem, again, I'm going to leave my answer kind of ugly. Taking my derivative, dv dt is now, so I had pi over 12 as a coefficient. 3 comes down in front. 3 over 12 is 4. That's h squared. Don't forget dh dt. Plugging in everything, dv dt was -80. Pi over 4. The moment was when h was 8. I want to know dh dt. So the rate of change of height with respect to time, -80 times 4 divided by pi times 8 squared. We don't like ugly answers, simplify it, but this is the change of height over time, and height will be measured in feet per minute. And of course, it makes sense that this is a negative rate because if we are draining water out, then of course your height would be getting smaller and smaller and smaller. Yes, Anna?
Could we either like leave the pi over 4 under the denominator, or can you not?
You could, I just don't like fractions and fractions. But any equivalent answer would be fine. So to me, that's like the hardest part of dealing sometimes with related rates, especially depending on some of these diagrams. When you have similar figures, I often have students ask me like, well, when do you know you need to use similar figures? And the short answer is like when you have too many variables, like you just need to get rid of variables, so you want to find some other relationship to simplify your equations with. Often shows up in problems that have like pyramids, cones, like prisms, three-dimensional shapes, have a lot of similar triangles, but then also if you have like overlapping shapes, like there's one on the homework that deals with like a man walking away from a light post, so you have like a smaller triangle and then a larger triangle. Yes, Avi?
Will the relationship always be like that easy to notice?
They should be pretty easy to notice, like similar figures. sound insulting, but similar figures, is just like a geometry topic. So normally it's just like, you just need to find the fraction that relates the two. Like this one was easy because a fraction of being like 1/2. I think that the most recent one I saw in the AP exam was like a fraction of like 3/2, but like it's never going to be anything too crazy. So that's
Mr.
basically
Brown,
related rates. Yes.
how did you get feet over minute?
How did I get the what?
The units, feet over minute?
So height would just be in feet, like area would be in feet squared, volume would be in feet cubed. So height would just be in feet, and then the time from the problem is just in minutes. So DH would be in feet, and then the DT is in minutes.
Gotcha. Thank you.
So moving forward, like I just want you to work on like your homework today. Your quiz is on Friday. Like I know it's like we just started this unit, but this unit really just has like 5 topics in it. So your quiz is going to just cover 2 topics. You have your derivatives of inverse trig functions. Just so you know how I'm going to be quizzing that on your quiz, there will be some questions that just say, hey, take the derivative, but then there's going to be other questions that say, find the derivative and maybe tell me where the intervals of increasing and decreasing are, or maybe find the derivative and write the equation of a tangent line. So like everything from this point on in calculus is going to be cumulative, just so you don't forget stuff, since there is an AP exam to worry about, or not really worry about, because you're going to do fine on it. But it is going to be a cumulative kind of stuff, so anything we have learned can show up, especially with the applications to derivatives. And then related rates, I have several different types of problems to give you to kind of cover like the variety of them. There'll be at least one that's going to be based off of like a very geometric formula. There's going to be another one that's more algebraic, like the ellipse one we did yesterday in the notes. And then there will be at least one where you will have to set up some similar figures to kind of condense the equation sum. So really I want you to use the rest of the class period to finish homework 1 and 2. Tomorrow I do have one related rates problem I'll use as like a warm-up, but tomorrow will also be a day for you to complete homeworks 1 and 2 as well. Matthew?
It's an algebraic one, will it always give us the equation?
Yes, because the equation will always be like the equation of the actual graph. All right, guys, so y'all can go ahead and get started on that. If you're at home and need my attention, just kind of raise your hand. I'll come over as soon as I can. But the quiz again will be on Friday, covering the topics on homework 1 and homework 2.